when looking at stars that are relatively close to Earth, there's another phenomenon that we're going to see, and that is that the old statement that stars are fixed on a celestial sphere is not precisely true if you look close enough. Of course, stars in general in the sky are in orbit. They're moving in all kinds of directions. They're very far, so their motions are typically minimal when you convert them to angular measures, but nearby stars, if measured precisely enough, are observed to move relative to the distant stars. This is called proper motion, is the term for the motion of the stars, and this is a motion over and above the annual oscillation that nearby stars perform due to parallax. But even if you subtract parallax, you observe that relative to the background stars, there's an ongoing continual motion. This is due to the actual motion of the star, so we can measure the motion of the star. It's characterized by the Greek letter mu, and mu is typically expressed in arc seconds per year, because those are the useful units for the typical orders of magnitude of proper motion. And when we're looking at an object, notice that an object can be in motion and have zero proper motion if it's moving right at us or away from us. And so when looking at an object, we define a plane called the transverse plane. The transverse plane in this image is this direction and the direction perpendicular to it coming out of the page towards us, and a radial direction. So there's a plane here, and then there's a radial direction, which is the direction along the line from us to the star. And we think separately of radial motion, that's motion towards us or away from us, which does not change the star's position in angular terms in the sky, and transverse motion, which is motion along the sky relative to the other stars. And proper motion captures any motion in the transverse direction. And we can convert, if we know the distance to the star, we can convert the angular motion, of course, to measure of its actual velocity, its actual transverse velocity, which is labeled by Vt. And basically the idea is, imagine waiting a year, the star's position in the sky will have changed by an angle mu. If we know its distance, which I call capital D, unlike this diagram, then the small angle formula tells me that the little distance d that it travels in the course of a year is d times mu. And this is its motion in what units? Well, if I write mu divided by 206,265 arc seconds, then this is a number. D will be in whatever units you measure capital D, the distance to the star, if you write it this way. But since this is in arc seconds per year, I will get an answer for the velocity. When this number is the distance the star travels in a year. That'll give me, say, parsecs per year as the units in which I measure the velocity. Typically, we measure velocity in more convenient units of kilometers per second. And so in kilometers per second, one finds that v in kilometer per second is basically given by mu divided by 1 arc second times d in parsec times a collection of conversion factors converting parsecs to kilometers and years to seconds. And the net result is that the conversion factor, you can do the algebra, is 4.74. So that's the meaning of this rather dimensionally confusing expression that we have here. This is how we measure a star's transverse velocity. A star can also have a radial velocity, and we can measure its radial velocity by measuring the Doppler shift. If you find some spectral line, we find its shift. If you're careful, you will notice that I have changed the sign here of the radial velocity relative to our convention. The previous convention that I used when I explained the Doppler shift is the one common among when studying sound. This convention is the astronomical convention. A positive radial velocity here means that lambda is bigger than lambda 0. That's a redshift. A positive radial velocity represents a star moving away from us, and that's the convention we will follow from now on, so that if I'm looking at a star and it's over here, then the radial velocity is a measure that I get from the Doppler shift, measures this component of its motion. The tangential velocity measures this component of its motion, and this represents a star that is doing both motions at the same time. In other words, moving in some diagonal direction in that way, and I can get a complete picture of the motion of the star. And just to give you an illustration of the dramatic effects over the long term of proper motions, most stars move relatively slowly, but if you give them time, things get interesting. This is an animation of the constellation that we now call the Big Dipper. This is not the way the Big Dipper looks. This is as it would have looked from Earth in 100,000 BC, were you to look up at it. And time runs rather quickly here, but you see the stars moving. We are approaching the present. Here we have the Big Dipper. The stars of the Big Dipper are a constellation. They are not a cluster. They are not near each other in the sky in any sense. And over time, their peculiar motions, as it's called, will completely change the appearance of the constellation. It will not stay the way it is. Stars do move if you give them time.